Welcome, welcome this evening to episode number 6, season 3 of the Late Night Conference. My name is Wilhelm Huck and I'm your host tonight. Welcome to people in the audience and also for the people watching online. Episode 6, that means that it is the season finale already. I can't believe that we went through this season so quickly, but we made sure that tonight we have a really special guest in the lecture present, who is actually a world leader on something that we haven't discussed so much before, because we have discussed AI extensively and how we can use AI in chemistry. But the big thing that is missing at some point very soon is data, because we chemists have done a lot of experiments, a lot of manual work, and we have thrown away most of the data. We haven't really gone through data in a very systematic fashion. And that is something that our speaker tonight, Professor Andy Cooper of Liverpool University, has realized quite a few years back, and he is really the world leader in putting robots in the lab, actual robots in actual labs. So it's promising to be a very exciting evening. Just to give you a little bit about background on Professor Cooper, he did his PhD in Nottingham University in 1994 as a Ramsey Memorial Research Fellowship to work with Andy Holmes in the Melville Laboratory for Polymer Synthesis. And that is exactly where I met Andy in 1999, where we very briefly overlapped, where Andy was working on supercritical CO2 and I was just starting out as a very young lecturer there. He then moved on to Royal Society EURF at the University of Liverpool, where he has been ever since. And he had really a fantastic career over there. He's been very busy, partially as head of department in chemistry and physical sciences between 2007 and 2012, but actually mostly busy setting up the Center for Materials Discovery. He was the director, the founding director, and he's still the director of the follow-up institute, that is the Materials Innovation Factory. He has been sort of building this Materials Innovation Factory to a very sizable institute with several hundred people working there, many robots of every kind of flavor, and I'm sure we will see examples tonight. He's founder of a spin-out company. He is a fellow of the Royal Society, won an ELC Advanced Grant, an ELC Synergy Grant, and many, many prizes and awards. I just mentioned a few: the Corday Morgan Medal, the McBain Medal, Tilden Prize, and the RSC Interdisciplinary Prize. And I think the last one is very fitting for tonight, because Professor Cooper has a background in chemistry, in all kinds of physical aspects, porous materials, and now also robotics and AI. And I should really not take up any more of his time. Professor Cooper, the floor is yours.
Okay, well, thank you, Wilhelm, for the introduction. It's lovely to be here. I'm sorry I can't be there in person, but I'll do my best over Zoom. So I'm going to talk about our work, recent work, in the area of computational discovery of materials and also using AI and robots. So just to set it up in terms of materials discovery, well, how do we discover materials currently? I've got 3 papers here as kind of examples of viewpoints. This one is by Tony Cheetham, Ram Seshadri, and Fred Woodall in UCSB. They published this paper last year, and they pointed out, broadly speaking, that actually most materials that are used in real applications, they weren't designed, they were repurposed. And they give a bunch of examples: perovskites, Teflon, and other materials. And I think it's an important point, actually. Many materials that are used in industry and in real applications weren't designed per se. They were found in some context, often basic research, and then repurposed into an application. Perovskites initially were not actually discovered as solar photovoltaic materials. They were found for another purpose, or maybe no purpose, I think, actually, and then repurposed as now a very important class of materials for photovoltaics. About 10 years earlier, 12 years earlier, Bob Carver published this paper. It makes the same point, perhaps in a similar point, in a different way. And he points out that for new technologies, and he focuses on solid state inorganic materials because that's his area. It may take many thousands of materials to underpin the pyramid that ultimately feeds through to be a new technology. Similar kind of point is things arise from this fundamental research space more than being purposefully designed often. And then the last paper, which is a little controversial and from 2006, I'll leave this for discussion, but Martin Jansen and Christian Schoen back then made an argument that actually design of materials is impossible. You can design a teapot, but you can't design a chemical composition. I disagree with this, but we can, if anyone's interested, we can talk about that. But certainly we would like to be able to design materials to shortcut this sort of pyramid approach or repurposing approach. So to build something in a computer, conceptualize it, model it, make it, and it does what you predict. To me, that is the ideal. And if you can do that well enough, in principle, you don't need robots. In practice, you can't do that for many materials, not yet, maybe never. So our program is, I would say, somewhere between digital design, kind of bottom-up approach, and discovery using robots. And as I hope I will convince you, maybe some of the most interesting stuff is somewhere in the middle, using elements of digital design and computation and elements of searching chemical space using automation. So roughly 3 parts: digital design, discovery using robots, and then sort of forward-looking things about work where we're starting to make these robots smarter and to work with humans. So here's an example of digital design. This molecule T2 was published in 2012 by Michael Massalertz and Iris Opel as being a porous hydrogen-bonded framework. And this is the structure. And as you can see, this is work with our collaborator, Graham Day in Southampton. We can predict this structure. So this is the predicted crystal structure, and it agrees with the structure that was published by Michael and Iris. And this is the predicted lattice energy. This is the density. And that was known as the structure for that material when we started this work. But we did crystal structure prediction, which is predicting the possible packings for molecules and calculating the lattice energy, which is on the y-axis here. And we found that actually it's one structure of very many possible structures, and it's by no means the lowest energy structure. So here we have a structure which is 50 kilojoules per mole more stable. But the thing that got us really excited is this structure here was predicted to have half the density and be a little bit more stable than the known form. And when we predicted this, there were no organic crystal structures in the Cambridge database with such a low density. So we thought if we can make that, that's going to be a record. So we did a lot of crystallization and actually found in the end there are at least 5 structures that you can make, including this one, which I think is still the lowest density organic molecular crystal. But there are 5 others, at least 5 others, including the one that Michael discovered. And it ranges from things which are totally dense to things which are essentially the lowest density organic crystals known. So you can actually discover a lot about these molecules from first principles, and you have a way to target searches in the lab. And you can see the agreement between the prediction and the experiment. So there are a few cases like this one where there's some distortion from the idealized geometry, but to all intents and purposes, the predictions are good enough to discover materials in the lab, and the powder diffraction patterns effectively match pretty much exactly with the predictions. So it's a map. It's an energy structure function map. In this case, the function is color-coded as the pore dimensionality, but perhaps more usefully, you can calculate anything that you can calculate from crystal structure. This is a methane deliverable capacity. So you can look at these 4 related molecules and say, well, actually, only this one is useful for methane storage, and only if you make that particular polymorph. And this is, in principle, extendable to any function where you can calculate the property from the crystal structure. Charge mobility, band gap, anything. if it's computationally affordable. And that's one of the challenges. You have a large number of structures, maybe tens to even hundreds of thousands of structures on the map, and the computational part may be expensive to calculate the function. So something we've done more recently is to sample these maps. Initially, we just calculated everything, which is very expensive. Now we're looking at ways to do sampling using something called Thompson sampling. It's related to Bayesian methods, which I'll talk about later, whereby sampling just a very small fraction of the landscape, maybe a fraction of a percent of the total landscape, you can still find, as you can see, the interesting structures. So this is a kind of atom-up design paradigm. You start with the molecule, could be a hypothetical molecule, a real molecule that you know can be synthesized, or something which you've just thought of, and you can get its structure and its function from first principles, go into the lab and make it. Of course, the vast majority of materials, unfortunately, aren't like that. So I could give a million examples here. I suppose a battery would be a good example. You can't design a battery from the atoms up. But here, this is a photocatalyst. So a semiconductor photocatalyst, which absorbs light to make a hole and an electron. And then there are a whole load of complex multi-length scale processes. The hole has to diffuse to the surface. The electron has to diffuse to a co-catalyst, and it's defined by things like the interface between the metal and the semiconductor, defects, particle size, and a ton of other things. Surface chemistry, hydrophobicity. I know in Nijmegen you have a strong interest in soft matter. It's a similar type of thing. Multi-length scale complexity, quite hard to design from the atoms up because of that. And I would contend we're not going to be able to design these sorts of complex structures from the atoms up for some decades, maybe never. So then you really need to do experiments, but also because of this multi-length scale complexity, the search space might be pretty big. So classical approaches to automation are some classical approaches to automation are shown here. Labs on tracks, ChemSpeed hardware. Stratios is a drug discovery activity in the US, finding candidate drug molecules. And of course, there are a whole bunch of other academic research groups in this field, Lee Cronin in Glasgow, the Acceleration Consortium activity in Toronto, Marty Burke in the US, looking at organic molecular synthesis by automation. There's some really great work being done there. But we are interested in material synthesis. That has some particular challenges. One challenge is it uses lots of different instruments. So in a materials lab, unlike, for example, biological screening, where you might be able to get your activity from one assay, in a materials lab, you're invariably needing to measure lots of things and lots of different properties. And, the scientific instrument market is projected to grow to more than $20 billion per annum. And all of those instruments are designed to be used by a human, not in a robot. So while you can automate in principle anything, it gets expensive, it gets costly, it gets complex, and particularly the more instruments you want to automate, the more complex and costly that gets. So our idea, sort of crazy idea at the time, was automate the researcher, not the instruments, and drop it into a lab which is as much as possible unmodified. So that was the genesis of what we ended up calling the mobile robotic chemist. So this was published, first paper was published in 2020. So the idea is we have a robot here that can work in a conventional, relatively conventional lab, as it were a drop-in solution. And as much as possible, not modify the equipment in the lab. As you see, we have to make some modifications in some cases, but where possible, we're trying to use instruments as much as we can without modification. So it can drop into a lab, work like a human. And crucially also think, if think isn't really the term, but optimize things in high dimensional space. And as I may or may not convince you, it did a PhD in a week. So this work got picked up by the press when it was published because it was in the first lockdown. So this idea of a robot that works by itself in an empty lab without any humans kind of resonated in 2020, and it got featured on the BBC News here. And they focused on the social distancing aspect, which of course is not why we built it. But this is Benjamin Berger, who was then the PhD student who did the work. He's actually Dutch, and he is now the CTO of our spin-out company. So what does it do? Well, it does kind of things that a human does in the lab: solid dispensing, liquid dispensing, reactions. This is a photochemical reaction. So we built this reactor block. Since then, there have been lots of things released actually commercially which do photochemical reactions, which I think if I were going to do this now, I would use a commercial photoreactor. And then measurement, in this case, GC. But that could in principle be anything. GPC for polymers, X-ray diffraction, I'm not going to talk about, but we're working on X-ray diffraction. NMR, in principle anything. This is gas chromatography to measure hydrogen production in the photocatalytic reaction. And this is the first reaction that we ever did, as it were, in anger. And you can see it was in April 2019. And it happened to be a bank holiday weekend here, so no one was in the lab. I'd like to say that's different from other weekends, but as you'll see, no one's in the lab. And what you're going to see is 48 hours of research condensed into about 2 minutes. You can see the robot working in the lab. The photocatalysis thing is in the foreground here. And every time this increments, it increments 16 samples because it works with a batch of 16 photocatalyst formulations. So you got the solid addition here, liquid addition. The capping station is actually the most complex thing because we had to cap the things under an inert gas, under nitrogen. So there we did have to build something different. This is the GC measurement device. So effectively everything is standard and commercial apart from this capping station, which we had to design to inertize the system. So you can see while I've been talking, it's gone through about finishes 196 samples in a weekend, in 48 hours. So for context, we were doing these things by hand before this at a rate of about 2 samples a day, using manual GC, manual injection, and so on. So it is 100 times faster, maybe more, and hence the PhD in a week. But the thing I didn't talk about is it's also optimizing, as it's not just carrying out a pre-programmed array of 192 experiments. It's running a Bayesian optimization algorithm. And embedded in this, I won't talk too much about the chemistry, but there were 6 hypotheses, effectively, ranging from change the catalyst concentration to the scavenger concentration. Then we had a hypothesis about dye sensitization, hypothesis about ionic strength, pH. This idea was my idea of adding surfactants. If you add a surfactant, you disperse the catalyst better in water, therefore it should work better. Turned out to be bullshit. It doesn't work. In fact, the surfactants are negative. And it turned out actually, as you'll see, the dyes also, although one of these dyes we had prior data to suggest it should work nicely as a dye sensitizer. In this system, it doesn't. And then what you do is you do what everyone teaches you in a chemistry degree not to do, is change everything at once. So the golden rule in chemistry is change one thing at a time. In this case, you change everything at once, or rather the algorithm does. So there are 100 million possible permutations of these reagents. So what it does is it does a certain number, I think 48 randomly, and then it proceeds to optimize the hydrogen evolution rate using this Bayesian algorithm. But you don't need to worry about that if you're running the experiment. Well, somebody does, but in practice, what you do is set it up, load in the solids and the liquids, and you run it. And then this is the catalyst activity as a function of sample number. This is how the space is being sampled. And you'll see over time, it optimizes quite quickly in this case. the black points are the baseline activity before we did the optimization. We ran that just to check stability of the system over time. And you can see after 8 days, it gets to a formulation of catalysts and other components, which is 6 times more active than the starting activity. And actually, the dyes are de-optimized, so are the surfactants. And salt is kind of neutral. So the way it works is salt actually is neither negative nor positive, but because it's not as positive as other things, it gets sort of squeezed out, as it were. And I don't have the slide, but actually it's quite interesting. Initially, the algorithm goes to a part of the space where it de-optimizes the base, sodium hydroxide. And then for about 150 experiments, it doesn't add any base. But then it comes back to it later, having removed some of the other components. So you can sort of see, you know, it works in a different way to human thinking. If you did 150 experiments with base and got the bad results, you'd probably stop. The algorithm doesn't do that. So it balances exploration and exploitation, searches the space. And one of the interesting challenges here is to know when to stop, actually, because the thing looks like it's plateaued. By no means is this the guaranteed global maximum, but we stopped anyway, largely because Benjamin Berger was running out of time on his PhD. But in principle, if you run it for another 6,000, experiments, you might get an even higher catalytic rate. And if you look at the stats for it, you can see some challenges here. You need to have very robust automation because it's going to be doing a lot of operations, 6,500 manipulations in 8 days. So what that means really is you have to have very low failure rates for the robotics. And it travels a distance of 1.4 miles. I can't give you that in kilometers because post-Brexit, we're not allowed to use kilometers. So this is by no means a standard approach, but just to give you a little teaser here, there are other things happening, and this is a large center in China, the USTC, University of Science and Technology in China, where they've repeated kind of similar workflow, and they're proposing to build a much larger activity with, I believe, hundreds of robots in a big building. So it's kind of exciting to see that. You can do other things. I will go fast through this. One of the more difficult things in automation is solid dispensing. It's very easy when you do it by hand, but it's actually quite hard to automate. So we recently, this just came out in Digital Discovery, built a dual arm robot for solid dispensing, which is better at dispensing certain solids, specifically very abrasive solids, which cause problems with a lot of the current solid dispensing technology. So this may be particularly good for things like solid state inorganic chemistry, where maybe all of the reagents are abrasive, granular, inorganic precursors, which maybe can't be dissolved or would be better used in the solid state. So this is a sort of biomimetic approach. It literally dispenses solids like a human. The interesting thing is if it over dispenses, it can tip everything out and start again, exactly like you would do if you did over dispense in your experiment. But as I said, these dyes are deselected in this experiment, but the robot doesn't know that they are dyes, and it doesn't know why, and it can't generalize. So in a sense, with this Bayesian optimization as embodied here, every time you do an experiment, you're learning all of chemistry again. So we're trying now to blend this with human intelligence, because AI, some people would not call Bayesian optimization AI. It's an algorithm, but algorithms are good at tasks which are largely complementary to human intelligence. The things that algorithms do well, humans do badly, and vice versa. So it would make a lot of sense to try to fold these things together. So something we're doing more recently, this is Abdul Latif who's leading this. So we're in this code which runs on a website with the idea of doing collaborative experiments where the optimizer and the human interact. So I'll give a really simple example here. This is a simulated football free kick, where you've got to kick the ball around the wall and hit the goal. So you can run this with pure Bayesian optimization with no knowledge of the physics. And after nearly 600 trials, you hit the goal. But then using Abdu's interface, you can interact with it. And by constraining it using your knowledge of football and gravity and physics, you can hit the goal in a third as many trials, which you might expect because, you know, you have some physics insight. The Bayesian optimization doesn't understand any physics. But one of the interesting things is the solutions reached are quite different. So the humans will tend to pick these sort of simple shots where you can intuitively say, yeah, shift it to the left a little bit. But won't select these kind of crazy loop shots, which kind of go up, you know, 6 kilometers in the air, come back down and hit the goal. But to an algorithm, they're equally probable or equally feasible, which gives you a sort of insight how these things might find chemistry solutions are different to the ones selected by humans, because humans do have a strong tendency to select simple things and also to go to operate what some people call confirmation bias, to select the things that you expect to work. So you can imagine how you might combine these two approaches by having a sort of interface where you can inject conjectures, if you like, into the optimizer to constrain it, maybe with very simple constraints like keep the catalyst concentration lower than X, or you can start to build up more complex conjectures like this surfactant is better than that surfactant, but only if the base concentration is higher than some number. And actually, you can kind of go on like this forever with nested Boolean conjectures if you wish. So we started to just trial this so far with some test functions, not chemistry. This is the Ackley function, a common test function. You can see it has a global minimum and lots of local minima. So it's a difficult function because you tend to get stuck in the local minima. Hence, it's used a lot for testing optimizers. And you can see this is the first implementation where Abdu simply allowed to put in some simple constraints, call them conjectures. They're really just constraints. So, and you can see as in 5-dimensional space, as you put in better conjectures, the optimization happens more quickly. That's what you would expect. This is the case with no conjecture or no constraint. And actually, if you go to 9-dimensional space, the no conjecture optimizer, it doesn't really even get off the baseline, whereas with your constraint, you find the optimum. But what's more interesting, of course, is in a real experiment, you won't just have one operator necessarily, and you may not only have one conjecture. And you can imagine a whole research team having a bunch of ideas, and some will be good and some will be bad. So how do you manage that? So we're now starting to look at ways to inject multiple conjectures. This is a really sort of simple mathematical case, though we're hoping to have a chemical case soon. So here we've got no conjecture, a weak conjecture, and a good conjecture. And what this does, what this optimization method does, is it's able to move away from what turn out to be bad conjectures. So the yellow points are the sort of weak conjectures. The orange points is, in this case, a good conjecture. The red points are where the algorithm is following its own course without using any conjectures. So it's effectively it ditches the weak conjecture and goes with the good one. This is an interesting. These are sort of weak and poor conjectures, and you can see it sort of eventually ditches both of the conjectures and goes with its own optimization. Now this is a simple case of 2 or 3 different conjectures, but this could be done with any number of conjectures. It could be 100, it could be 1,000. And we're looking at ways to figure out, well, if you have a multiple pool of ideas, and some of which may be directly orthogonal or self-contradictory, how to manage that. So this is the idea of human in the loop or crowdsourcing ideas. And there's a whole literature around this, actually, in the so-called wisdom of crowds. You can find 100 quotes on this. Charles Bukowski. He wasn't a big fan of the wisdom of crowds, as you can see, though he was a controversial figure. But this is the quote that I like perhaps the most from Kennedy. One person can make a difference and everyone should try. So basically the idea is, if you have your pool of researchers, it doesn't matter if most people have bad ideas, as long as somebody has a good idea, because we build a system where the good ideas will be selected. So that's hoping to have a physical example of this by the end of the year. The other thing we're trying to do is to directly fold in the first part of the talk is to have physical models, computational predictions directing the robot. So physics-based models directing the search. That's something we're doing with our collaborators in Southampton and also the University of Rostock in Germany. So in the end, we got a sort of vision that you might fold all of these things together. So imagine a robotic experiment searching for things in the lab. This is actually an implementation of a ChemSpeed, where a robot using a robot, where the mobile robot uses a ChemSpeed robot. And then you can visualize the evolving data. A challenge in itself when you have high dimensional data, and to have a good visualization method, that's not easy. It's also a challenge. Then you can inject your insight perhaps as a team, and then may also have computational guidance from physics-based predictions such as crystal structure prediction and other predictions. So the vision for the future is folding that all together in one experiment, and that would be genuinely new if we could do that. Each of those bits has its own challenges. So that's the summary. We'd like also to sort of make this as kind of global idea is, of course, the experts do not have to be in one place, have a web interface for this. The knowledge could be injected from anywhere asynchronously. It doesn't need to be in the same time zone necessarily. So that's the kind of vision for the future. And finish with some acknowledgements. All of the work on crystal structure prediction was done with Graham Day in Southampton. I didn't talk about Vitaly Kurlin, but we're working with him on some elements related to crystal structure prediction. And people involved: Benjamin Berger, Abdul Latif, I mentioned on the human in the loop stuff, Vlad and Xenophon. Ying worked on the solid dispensing with Louis. Hartem and Gabriella are roboticists in the group who've helped with much of the robotics work. And Amy is working on, didn't talk about her work, is working on automating powder X-ray diffraction. But thanks again for the invitation, and happy to answer any questions.
Andy, thank you so much. That was a truly fascinating and visionary lecture. Thank you so much. I think the idea that you essentially had several years, all those years back, to automate the research and not the equipment is brilliant. And I think you've shown us that it was a brilliant idea. I think you have pushed it very hard to really sort of make that robot take over a lot of the daily routine work that I would have expected would be difficult to do. And then I think you close the loop in the end where you show that the robot is operating the ChemSpeed robot. I think that's clearly demonstrating how far the system has come. So thank you for that. There will be questions from the audience. I'm looking around. There's already one question in the Zoom. Sovik says, very impressive progress. I have a technical question. Sample preparation is different from different types of machine. Does the robot need optimization for all types of measurement and or experiments?
Yeah, that's a good question. Of course, I mean, that's a very broad question. I mean, there's some nice work that's been done on automating, for example, spin coating for photovoltaic materials in Erlangen University in Germany, and other thin film work in UBC in Canada. I mean, the answer is yes, of course. I mean, if you want to assemble a coin cell, a battery coin cell, that's a different set of operations to solid dispensing or liquid dispensing. But I I mean, I don't know how to answer that other than in principle, anything can be done, but there might be some operations where the effort to automate is so great that it may be quicker to fold in sort of a mixed experiment. Humans do some of the work, robots do some of the work. And I guess it depends how long you're going to do it for, right? If it's a 6-month campaign, you almost certainly wouldn't build a machine to do it. If you're going to do it for the next 20 years, then you might, and there are indeed automation examples of coin cells and batteries. So I don't know. It's a very hard, I think the honest answer is some things are much easier to automate than others, and it depends.
Maybe to follow up on that question, because if you think about the ChemSpeed system, it's obviously completely fixed. So it's Swiss engineering. It does exactly what it is supposed to be doing. For your gyro robots, would they be self-learning? So if I'm thinking about the video where you show that the robot is dispensing a solid, suppose it realizes that it is a very sticky solid. Will it change the type of movement it makes to make sure that it still gets something out of the bottle?
Actually, the thing I showed, the 2-arm robot, it already has a degree of that kind of logic in it. But that particular system uses something called fuzzy logic, which is a sort of much older method than reinforcement learning. It's been around since at least the 1970s. But that works quite well, actually, the fuzzy logic controller, which is also used in washing machines and things. But the answer is yes, we'd like to do that. When we're beginning to do that, it's quite difficult to do it generalizably, sort of to capture any possible context. But for sure, that's where we see it going. And we do have some examples already where sort of set this idea, it's a common idea in robotics, a very big theme in robotics is self-learning, supervised learning, and more topically unsupervised learning, where the robot just teaches itself. The most well-known example is the robot that will balance a stick, and it takes a few hundred iterations, and then it can balance it indefinitely by unsupervised learning. And there are chemistry equivalents of that. So yeah, we'd like certainly, yeah, the idea of robots that actually get better as they learn the task is really attractive. And currently, automation systems, the chemistry systems have a degree of that functionality, actually, of self-optimization. And yeah, we'd love to do that in the future. And I think we can borrow a lot from the robotics community, because that's a major theme in robotics. Yeah.
There's a question in the audience. Will?
Hi. Yeah, thanks for your talk. Thanks for taking the time. We're really enjoying it on our side. So I was interested in the conjectures that you mentioned and the human in the loop ideas. So the conjectures look somewhat like natural language. We've seen a lot of smiles in the late night conference this season. There's Lee Cronin's KDL. So how do you envision humans in the loop communicating with robots? Do they use something like programming, or do they communicate with natural language? How do you see that going?
Well, a good question, and not an obvious one to answer. I do think the answer, though, does need, it's my personal view, I think the answer does need to be something like natural language. The reason is, when you talk about chemistry, you tend to say, this reaction happens, works better under basic conditions. You don't tend to say, this reaction works best at a hydroxide concentration between X and Y. You just don't tend to do that, So to have something that can work in sort of more general terms, I think is more powerful. Not least because it's a limitation to how we can think, Similarly, we work a lot with semiconductor materials, and you tend to say they have high, medium, or low band gaps. You don't tend to be able to say it's between 2 and 2.05 electron volts. So yeah, I think it needs to be something like it, but then it depends on the problem, I guess, because for some of the work Lee and others are doing is retrosynthesis of organic molecules. That's a different problem, right? But I think for the work we're doing, at least, I think a natural language interface would be where we're leaning towards, but exactly what form that takes, we're still working on that, and it's not obvious.
Okay, very interesting. Thank you.
I'm looking at the audience. Timon.
Thank you very much for your fantastic. I'm very interested in like your idea that to design a chemical brain. Then I'm wondering what is the goal that you want to achieve to design a chemical brain, and yeah.
Yes. It's an easier term to say than to explain, I guess. I mean, I suppose what we mean is at the simplest level, to be able to understand that different things in a reaction have different functions. So at the lowest level, it's like, well, this is a dye. So if this dye is good, then possibly other dyes are good. But then the first thing you need to understand is that the thing is a dye. So in the optimization I talked about, every component is just a component. It's just, component 1, 2, 3, 4, 5, 6. They're not even in classes. So the lowest level, I suppose, is to classify things. So this is a semiconductor, this is a dye, this is an acid, this is a base. But then you can build, so that'll be the lowest, maybe one of the lower levels of intelligence. So the robot could learn, well, actually, not that component 17 is bad, could learn that dye is a bad and generalize and then build up from there. I mean, I think initially they will be the sort of baby steps, is sort of that's actually what we see as the first level. You could imagine a scenario where, of course, the robot consults the literature and forms its own conjectures and then sort of reads the literature and chooses its own experiments. And then there's no human input at all. But I think, hesitate to say that won't happen, but I think that's going to take a little time. But so that's how I see it evolving loosely, is sort of start with some simple. Right now, a lot of the work in self-optimizing chemistry is not really contextual. It's sort of, there are 6 components and you find the best mixture. That could be making a cake or anything. Right? It's not chemistry, it's just optimization, which is what we did too. But if you get to larger spaces and more complex spaces, then that starts to become impossible, because you might have 100 components and you can't, I think, do 100 variable optimization. You just can't do it because it's too big. I don't know if I answered the question there, but I guess the answer is sort of build an initial framework first. So a lot of this is, a word that people like to use is ontologies. Yeah, it's on having ontologies. Language is one ontology. Smiles is a different ontology.
Andy, following up from this idea, because at the moment you essentially say, I'm going to automate certain processes in the lab, where you say the human has to do a lot of tedious work, and you make it easier, and you make it possible to move through a much bigger parameter space. But the research, the robot is not really doing science at the moment. I think that was what you were trying to say just a second ago, where you said, well, the robot doesn't know what a dye is, so it doesn't really know that if it is excluding a dye, that has a certain consequence. Would you say that in the end, your end goal would be that the robot is really doing science? So you say, you just give it a task to say, discover a new photocatalyst, but you don't tell it actually what ingredients it should be using. So it will actually search in the cabinet for the right ingredients that it could start with, and then and develop its own experiments.
Up to a point. I mean, I know a lot of people get quite upset about the use of the term AI, for one thing, and what is AI anyway? When is AI? That's a question. Sort of. Certainly at the level of, a kind of reasoning. I would hesitate to call it doing science, actually. And you could make some conceptual analogy with large language models. So ChatGPT, it looks like it's intelligent, but at some level it's making extrapolation between very large data sets. So imagine a system where, the system could understand that a class of components, which you've told it that these things belong to a class, and that class, by implication of experiments that it's done, the other things in the class are probably negative. for example, dyes, bases, you know. So that's a kind of low level of reasoning. So I'm not sure you call that doing science, but it's certainly closer to doing science than pure optimization where everything is just variable X, Y, Z, and so on. I think that's kind of the next step. Then there's a longer term question about when does it, you know, there have been some meetings in the UK organized by the Turing Institute, is like, and the title of the series of meetings is, could AI win the Nobel Prize? And that's a different question. But I think we're going to start, I mean, I would say you can go a long way by applying sort of more constraints to the optimization. It's not intelligence, but it's certainly a lot more intelligent than brute force optimization without any ontology. I don't know if that answers the question. I think it's going to be a long road before we have, you know, robots, you know, emailing us saying, well, actually, here's my grant proposal, right? I mean, we're a very long way. I mean, these systems can't even produce, you know, they can't produce new hypotheses. You know, it's sort of pretty low level, is working within the framework of what it's done in a closed loop experiment. Yeah, not knowing any chemistry. So I think it's important we don't overstate what that is, but it's a lot more intelligent than something you just program and it does what it's told, right?
I appreciate it's a far way off, and actually you just mentioned the research proposal. I guess we will have AI that will write the research proposal for us as well. But would it raise some ethical concerns or general concerns? Because as a PI, you're probably sitting in your office and not doing actual experiments. So you might say, well, it doesn't matter to me so much whether the robot is doing the experiment or the PhD student or the postdoc. But I'm sure the people here just in front of me in the audience, they would beg to differ. It matters a lot to them. So what does this mean? Are we going to sort of change the whole way we educate people and change the way we really also have PhD students working in the lab?
Well, I think it could change some aspects, but certainly I don't see it as sort of blunt as, well, this replaces PhD students, because it really doesn't, you know. You still have to come up with the idea for the experiment in the first place, which really is, in many cases, that is the hard bit, is deciding what to work on and why. That's really the hard bit, you know, often. So you still have to do that. And it's still going to be the case that the smartest ideas prosper, because it's just, you have a way to search more things more quickly with, I mean, I think of it as sort of a way to assist people, not replace people. I really do. And you know, these systems are so far off coming up with their own wholly new ideas, you know, bridging concepts between different disciplines. They're not even at the moment nowhere close to doing that. So I even in a world where everybody had one of these systems, imagine that everyone had one of these systems. No, I don't think fundamentally it changes things. People maybe need to start thinking about how to sort of search larger spaces and define the problem, like what variables should we be, you know, what are the variables that it sort of changes the problem, right? You have to think about what variables should we be changing and why, which I think is often the most difficult thing about doing research anyway, is framing a good problem, right? And then the robot does it faster. But no, I don't think it's going to make that kind of difference. And nobody ever asked that when we, you know, had a GPC auto sampler or something. As always, oh my God, is this going to replace polymer chemists, you know? And at some level, it's a sort of extension of that, really. And in that sense, automation's not a very new thing. You know, auto samplers didn't kill organic chemistry. Right?
Quite clear.
Not yet. I mean, there's always time. Fingers crossed.
considering the skills that people might need to work in a lab where you also have robots and a lot of robotic systems. So, for example, in your lab, would you have sort of people with a computer chemistry, engineering background, or would it really much more that the chemists actually learn how to build the robots or modify the robots? How does that work out in practice?
Well, originally we were all chemists, and Benjamin, who joined the group, had a MSc in computer science, but he was also effectively chemist, really. But now we have a mixture of roboticists and computer scientists, and it is much more effective because it's hard. You can only go so far with only chemists. So we now got robotics people in the group and computer scientists, and that's made a massive difference. But the chemists still, I mean, some of the chemistry PhDs are doing some pretty advanced things as well, actually, and they've picked it up and really moved things forward. But yeah, I think realistically, we're at the stage at the moment where this stuff it's a bit difficult to do without people with robotics is a whole discipline, and I'm not a roboticist, right? So I couldn't do this stuff by myself, no.
I'm looking around the audience to make sure. Timay has another question.
Maybe I have another question. Yeah, just I think the most important for research is to ask the research question. I'm wondering what the robots in the future can figure out which the research question is most important for us to study and then guide us to do the science.
Yeah, I mean, my guess is at some point that will be feasible, but I think we're quite a long way from it at the moment. Actually, if you look at the sort of tools available in AI at the moment, but it's a very interesting direction. My guess is it will evolve in steps. We're not just going to go straight to a scenario where AI is deciding what questions are important. But you could imagine a future where, I think if we get there at all, it will be via a sort of situation where people are using AI advisors to help them make decisions, which already is very much what, some people don't like ChatGPT, but that's what it does, right? You ask it questions, it won't give you an opinion. It will say, well, here are the considerations, in order to design a catalyst, the things to consider X, Y, and Z. It will just give you a big list of considerations, but it won't tell you what, and even if you say, please prioritize these by order of importance, it will give you some answer like, I am an AI, I cannot, I do not have an opinion. So I think at the first step will be AI type advisors, I guess. And then maybe in the future, yeah, there might be a scenario where everything is fully autonomous, but I genuinely feel we're a little far from that at the moment, though it is a very interesting idea. But it's a dangerous thing to predict what can't be done, and many people are made fools by doing so. So I'm not going to say it can't be done.
We have another question we have a question in the audience and then in the chat.
Presentation. I have a question because when it comes to solids, you said that when it comes to measuring, it's something that actually preparing, it's something that it's fairly easy for a human, but not necessarily for a machine. And I was wondering if there are any other typically technical procedures that are also way easier for a human than for a robot, even though for me, it was surprising. It was counterintuitive that it would be so hard for a robot.
Well, yeah. Well, I think it's easy to sort of not realize how much sort of people, when you do these tasks, you do them basically automatically. You don't think about it really, But if you're doing something even as simple as weighing out a solid, there's a lot going on. You're looking at the spatula, you're to some extent doing it by touch, by eye. Different people do it different ways, but there's a lot of feedback. Actually, it feels like a simple process, but not that simple. And if it's a sticky solid, then you sort of scrape it from the pot and scrape it onto the side of the vial, right? And you make a decision. You don't even think about it. So there's Wilhelm's question. I mean, we do that stuff all the time. It's just trivial. A baby can learn to catch a ball in 1 or 2 attempts, but AI still can't do that. So you have a physical understanding of it's sort of partly linked to being a human and having a body, right? So So yeah, there are lots of examples actually. I mean, I would imagine, I've never tried, but if you ask a robot to assemble a sort of complex ground glass quick fit, glassware, it wouldn't do very well. So even really basic things, fluting a filter paper. I don't know if I'm showing my age now, but that kind of thing, fluting a filter paper. Think of a million examples. Anything that requires moderate dexterity actually is hard for a robot. So humans are not dead yet, actually.
I'm sorry.
I mean, you can, you still got robotics labs effectively working out how to carry an apple across a lab. So we're not going to be redundant anytime soon.
It feels that this is not the direction of the discussion we should be having, right? Because now it sounds like we should not automate the researcher because that feels too difficult.
Have I completely undercut my own program? No, no, of course. The thing about it is once you have a robust method that works, it can be very robust, right? So it might be difficult to do it once, but once you have something that is robust, then you do it 10,000 times. Right? So no, I know. I just, I guess the point I'm making is sometimes you don't want to literally translate what the human does. That's just not the way to do it, Though I did give an example of that, but sometimes the better way is to do it in some totally different automated way.
There's a question in the chat. Jose is asking, given the goal-driven orientation and optimization of processes, what would you say is your personal end goal of automating scientific discovery? I guess you have mentioned many aspects of that already, but maybe sort of to summarize.
Yeah, I don't even know if I have that as an end goal. I mean, I should say we started this because we were interested in photocatalysts for water splitting, actually. We didn't come at it from the automation side. We were working on that for a long time before we did this robotics work. So it really came at it from the sort of how to do that workflow for that chemistry. So I'm not sure I have an end goal. That's a fairly uninspiring point to end on, but I've become very interested in what we can do. I suppose my end goal, if I have an end goal, would be to try to fold together this human and algorithm decision making. I think that's probably my next goal, maybe not my end goal, but that's my next goal.
I see that we're running close to the end time. There's a question in the audience, otherwise I think I would like to end with a very general question. There's none in the audience right now, and I think this is the question that we haven't asked so much in this season, but I think in this final episode is a fitting one. And also knowing your background in various fields of chemistry, one of the questions we would like to ask also to give insight for the younger people in the audience, where we say every scientist has individuals who are important to their career. With regard to those who have helped you over the course of your career, and you've had many different sort of directions that you explored, how did you meet and develop sort of the professional relationships, and what has been sort of the main guidance that you have experienced?
Well, that's a very hard question. I don't know. I think I was influenced quite a lot by my PhD supervisor, Martin Polyakov, actually. He was always sort of interested in everything. And I think that probably influenced me a lot. And I don't know if I finish on some advice. It really is important to work with different people, different disciplines. That's perhaps the most enjoyable thing about the work we've been doing recently, is talking to people from different areas of different perspectives, and if you're in science for a long time, it's important to have new experiences and do new things. I was nearly 50 when we started as mobile robots work. So, I think you've got to keep changing it up. And that's ultimately the fun bit, is working with people and exchanging ideas. That's, I think, why most people do science in the end.
I think that's a very nice concluding statement to this episode and to this season. I would like to thank you also on behalf of the audience for a fascinating presentation showing us what is possible combining robotics and AI and chemistry. We're looking forward to further contributions from your lab, and we hope to learn quite a bit from your sort of insights in robotics, and hopefully we can implement them here in Nijmegen in the Netherlands very soon. Thank you again. So thank you.
Thank you.
And with that, we conclude this episode. We conclude the season. Thank you, everyone watching, also here in the audience, for being with us for the last 6 episodes. Thank you for your questions. Right now, for us here, it is time to have some drinks. Andy, thank you. It's probably dinner time in the UK by now. And I hope to see you all back in the new season next year. Thank you all.